Okay. Next up is TJ Sego. He's a professor at the University of Florida, and he does a lot of tool development, I think originally from multi-scale agent-based modeling. But lately I think he's going to talk more about dealing with the results of these models and specifically stochastic simulations. Is that right, TJ?
That's right, Bart. Thank you.
Yeah. Okay. Take it away.
Great. Thanks very much, Bart, for that introduction. And hello, everyone. As Bart said, my name is TJ Sego, Assistant Professor of Medicine at the University of Florida. And very happy to be talking with all of you today. I'm going to assume that you can hear me okay and that you can see my screen. If that's not true, then please someone stop me. Otherwise, I'm going to proceed and just get right into it, which is a discussion of this new work that I and some collaborators have been working on dealing with the issue of reproducibility of stochastic simulation results. And I guess I should say before we start, I do not mind being interrupted for questions, whether they're in the chat or if everyone's allowed to unmute. Also welcome just unmuting and chiming right in. Otherwise, we'll just proceed right through this. And yeah, so to give you just a bit of background on the motivation here. So I'm going to assume that there's been at least some discussion throughout this workshop on the biomodels project and all the great work that's been done between biomodels and biosimulators. But just to say that I did. This project is very strongly motivated by biomodels and extending its current capability and the services that it provides to the general public, specifically on their curation and verification processes for reproducibility. In particular, this project is very much motivated by extending biomodels' capability to reproduce stochastic models or stochastic results from doing interesting things with deterministic models. And so to that effect, I want to just give an acknowledgement to the ever-growing list of people who have contributed to the ideas and the work that you see here today. And this list here on the right is really generous when I say contributors and collaborators, and that some people on this list have just attended some of the workshops that we've organized and listened to the work and told us where it's good and where it's bad. Others have actually been working on the software library that accompanies this. But in particular, my main collaborator on this has been Raman Sharif at EMBL EBI, the big biomodels boss. This was all motivated by a talk that he gave just over a year ago back in Paris. And we've been working at this problem and continue to do so. To that effect, I wanted to start off by providing some resources. So everything that we will discuss today is all open access, all freely available. I will put links in the chat here for anyone who's maybe trying to furiously type some of this information. So we very recently published a preprint that describes the gory details of what will be discussed today. I don't intend to dive too much into any particular facet of this work. There is some intensive mathematics and statistics. I think the software work in particular is really cool. But I don't want to like dive into any particular part of it per se, but instead just give a sense of an overview of what we're doing, you know, what's on the horizon for this work and what we can currently do. And I'd also like to point out that everything that you see here today concerning ODE models, this was all done with Tellurium. So all of the simulation results that you see here were generated with libRoadrunner in Tellurium. All of the specifications are described in antimony. So with these links and the stuff that you've learned throughout the week, everything that you see here, you can do right now. So if you're working on some stochastic models or doing some stochastic sampling of some deterministic models, say listen closely to the extent of maybe considering that some of this might be relevant to some of the research or say interesting project work that you're doing right now. That being said, let's dive into this. So stochastic results, it's an interesting problem to ask really what it means to reproduce results that are stochastic in general. And there are a lot of aspects to this with some subtleties that I don't want to get lost in the details of it, but I would like to at least convey a sense of what the real problem is here. And to give you a sense of the relevance, at least in the world of ODE models, we are particularly concerned with reproducing time series data with stochasticity. And you can see some examples here. This is, again, these are tellurium results. Here on the left, this is the Lorentz system with Gillespie stochastic simulation algorithm. Here on the right, this is a deterministic model, but with random sampling of initial conditions. Both of these are within the scope of our problem domain. And what we're particularly interested in is to provide the ability for someone in independent study to verify that they can reproduce results like these as found in publications or say made available in biomodels. And a couple of subtleties of interest that I do at least want to point out. For one, it is theoretically possible to reproduce individual trajectories that are shown here. Every gray line that you see is a different realization of the same model, same sampling distributions, and just run repeatedly and plot on the same graph. Here in this top row, this is with a sample size of 10. Here on the bottom row, this is a sample size of 10,000. It is theoretically possible to individually reproduce every single one of these trajectories under very idealized circumstances. That is not the problem that we are interested in. We are interested in the problem of producing results that are sufficiently representative of the system in a reproducible way, and then enabling others to verify that they can also produce those same results in independent study. And a lot of times I like to refer to this as comparing hairballs because with a lot of results like these, this can get really messy, especially with complex systems like in the multicellular and multi-scale modeling that Bart had mentioned and that was previously discussed. These results can get really messy, and a lot of times it's really unclear whether or not results that are even published are actually representative of the system, let alone trying to compare, say, a hairball that you've generated on your computer to a hairball that's published in a paper. How do you know what's sufficiently representative, what's reliably reproducible, and how especially do you quantitate the degree to which the results that you have on your computer are the same as the results that you find either on biomodels or in a paper. There's an obvious question that comes up just right off the bat, which is why not just use summary statistics for solving a problem like this? If if we generate trajectories like, again, what you see here in this example, these are the same model and some particularities that we'll discuss here in a moment. But there's the question of, well, why not just calculate the means and standard deviations or variance or some other summary statistics that could say sufficiently convey a sense of like how close results are between two different implementations. And in a lot of cases, that is sufficient. SBML Test Suite does this and does a really good job of this for SBML models. But there are issues to do with more general purpose applications where summary statistics just are totally insufficient. The obvious example that comes up is that for lots of different kinds of distributions, summary statistics are like, say, variance are just not defined. In other cases, it's just really not clear, say, with comparing like the difference in means between two implementations, what is, say, a sufficient relative error when calculating the difference between two different implementations. most importantly, one really has to have a real sense of what their results actually are before deciding what summary statistics would be sufficiently representative of those results. And in the conversations that we've had with, especially with modelers in these, some of the community facing activities that we've done, a big issue that comes up from modelers is that summary statistics just don't accurately convey their data. If we jump back a slide, say to this system with this bifurcation, an average here is just the value of 1. And a lot of modelers really take issue with trying to describe like the overall behavior of a model like this, with a summary statistic that just doesn't convey at all any sense of the actual dynamical behavior of the system. And so we kind of began right off the bat just deciding that we were going to try to look for something a little more general purpose. And I've given kind of an elementary example to demonstrate what this can actually look like in practice. So this is a simple ODE model of epidemiological model of viral infection. And the trivial example here is that one of these variables is being initialized in each of these rows with a probability distribution function. So the initial condition for this variable V is randomly selected from a probability distribution function. Each of these rows uses a different probability distribution function, but they're all designed to have the same mean and standard deviation. And we find when we go through and say, what is this? This is a sample size of 10,000 simulations per probability distribution function. We calculate the mean for all of them, totally indistinguishable. It's a deterministic model, probability distribution function for initial conditions with the same summary statistics, but are distinctly different. I mean, even by inspection, these are different results. And yet the ability to detect those differences, not reliable. So our jumping off point then is towards what we actually did, which the brand name that Sharif came up with for this, we call it EFFECT, which is short for the Empirical Characteristic Function Equality Test. And that really is to say that our solution to how to quantitate differences between samples taken from either stochastic models or stochastically sampled models, we generate characteristic functions that characterize those results and then compare them between samples to determine whether, say, two samples are the same statistically, or in some other respects to determine how reproducible a particular sample is. Now, the important features here for now, we'll get into the details a little bit on some of the, the big words that I just threw out, but the important points to point out for now. So this is a data-driven test for equality in distribution of results. And that is what we are looking to solve. Given two samples, how equal are they in distribution to each other? Sometimes we refer to this as statistical equivalence, but the mathematical definition is equality in distribution. The other important feature here, at least for now, is that this supports all real valued results. So we will look a lot at ODE models, and that's mostly as a matter of convenience because Tellurium Simulator is lightning fast and best in class. But this is also applicable to any other simulation results that are real valued. We'll see this a little bit. We do some examples with some other methodologies. Don't assume, given that we look at a lot of ODE models, that this is only relevant to ODE models. And so the questions that we really want to address, for one, as a modeler, when generating results, we want to address the question of when is a sample size sufficient? And you can see a really good example of this in this re-implementation of a co-infection model by Amanda Smith and Amber Smith. So this is increasing sample size for this model. And you can see that if I were to report this sample here of just 10 simulation replicates, not particularly representative of what the actual system is. And if one were to generate another sample of just 10 simulation replicates, one would expect that there would be a lot of differences when comparing the first sample to the other. So the first question we want to address is, at what point is a sample size that I've generated sufficiently representative of my model so that someone else can reliably reproduce my results? Second question, once I've generated a sufficiently representative sample, how do I package the data and information to enable others to reproduce my results? And third, as an independent, say, curator, given a sample of stochastic simulation results, how can I tell whether my implementation produces the same results as given results from, say, a biomodel submission or as featured in a publication? And so we break this down into two problems. The first one is kind of the classic one that biomodels does every day, and we call this the curator's problem, which is the problem of reproduced results. It's the one that I just described. So given a set of simulation results, how can I tell whether I have reproduced those results with my own implementation of the same model? But in our work, we have an additional step, so a second problem that we refer to as the modeler's problem. And that's the first one that we previously discussed. And that is the question of how can I tell if someone else can reproduce my results? So the modeler's problem is on the burden of a modeler, and the curator's problem is the problem that biomodels deal with every day. And here's an overview of the approach. So I'd mentioned characteristic functions previously. This is an overview of how we arrived at this approach. And all math aside, you could just sort of visualize this by looking at this progression of increasing sample size. So we want to test for equality and distribution of results. And a really good way to do that is to evaluate probability distribution functions that are generated from a sample. So what you see here by row, sample size 10, sample size 50, sample size 10,000, this is just a histogram. Simulation results, the likelihood of finding each of these variables at some particular value at a particular time. And what you'll notice when you go through this procedure with every model like this is that as you increase the sample size, eventually the probability distribution function stops looking different, which is to say that the computed probability distribution function converges to the actual probability distribution function of the model. The issue with using probability distribution functions is that it's not particularly convenient. It's actually really hard to standardize a test that's built on empirical probability distribution functions, how to package this information and standardize a workflow based on this really became intractable really quickly. And so we migrated to the solution of the characteristic function, which has a direct relationship with the probability distribution function. If you're interested in the math, my email is in a couple of slides, and you have the link to the paper, and I would be happy to discuss the details there. But suffice it to say that there is a straightforward way to compute a complex valued function that has a unique one-to-one mapping to and from the probability distribution function. And as it turns out, this characteristic function is way more convenient to deal with in terms of packaging data, standardizing a workflow, sharing, reproducibility, like supporting data. All of this becomes really straightforward when using these, specifically an empirical characteristic function. And some of you may recognize this as the Fourier transform. The explicit like analytic expression for this, it is a Fourier transform of the probability distribution. If that doesn't mean anything to you, that's fine. It's not necessary to understand this, but suffice it to say that there's a clear parallelizable way to algorithmically compute these empirical characteristic functions just by doing a summation of an operation on a sample at each simulation time. That is the values that you see here. It's performing this operation on all of the replicates at each individual simulation time. And most importantly, you also notice a convergence behavior in this plot here. So this is looking at a simulation time of around 4 for this variable S. And what we're looking at is the empirical characteristic function for each of these samples. And most importantly, you'll notice that as the sample size increases from blue to orange to green to red, this is converging to the actual characteristic function. And that's the behavior that we want. Want to use this procedure to determine a sufficient sample size such that the characteristic function that we compute is sufficiently close to the actual characteristic function, and then use that to compare these computed values from different samples. again, feel free to interrupt by unmuting if you're allowing that. I forgot to ask, sorry. Or just enter questions in the chat. Otherwise, I'm going to continue and assume that everyone's with me.
Yeah, people can interrupt those at will.
Okay, cool. Thanks, Lucian. I should have checked. Sorry about that.
No, it's fine.
Okay, so continuing on with, if I remember correctly, this is the last bit of like real math here. I want to define then a measure for how to compare how sufficiently close two empirical characteristic functions are. Again, our representation of a given sample is with these empirical characteristic functions. And so we want to define a scalar valued metric to determine how similar characteristic functions for two samples are. And this in practice is something like the Kolmogorov-Smirnov statistic, for those of you who like statistics. In theory, it's really what we call a pointwise convergence in distribution. Most importantly, what you see plotted here, this is computing the what we call the effect error, which is this error metric for comparing two samples. You'll notice that this effect error is decreasing with increasing sample size. Now, importantly, one of the really nice features of this is that the empirical characteristic function, or just characteristic functions in general, so these are complex valued functions that are bounded with a magnitude in 0 and 1. And that means that this error metric, regardless of the actual source of the, like the source model, the error metric is bounded between 0 and 2. So whether you're using results from a multicellular, multi-scale model, or an ODE model, or Boolean network model, if you have an error metric value in hand, that has the same meaning as comparing samples from other source models. So there's no normalization required here. The normalization is done by computing the empirical characteristic functions. So one can have a general sense of how similar two characteristic functions are, and thus two samples, just for a given effect error. All right. So let's proceed. This is our solution to the modeler's problem, which again is well described as just asking, can someone else reproduce my results? So given a model and performing some procedure to either have stochasticity in that model or do stochastic sampling of a deterministic model, you're producing stochastic results, and you want to determine how large should my sample size be to report in a publication or to submit to biomodels, to where someone else can reliably reproduce my results when implementing my model and producing a sample of the same size. We call this the test for reproducibility. And the procedure is fairly straightforward. So the procedure in general is to start by choosing a particular sample size. And we can just walk through this here visually, say starting with a sample size of 10. So run your model 10 times, generate 10 replicates, divide your sample randomly into equally sized subsamples, and compute the effect error. That is the distribution that you see here. Randomly selecting equally sized subsamples, compute the distribution of the effect error, and then continue to increase your sample size until the distribution of the effect error satisfies some criterion. And I'm going to be purposefully ambiguous on what exactly that criterion is, because this is a subject of current research on this particular topic. Suffice it to say that as one increases the sample size, one will find that when randomly sampling the effect error, it will tend towards 0, and narrowly so. What this describes is the likelihood of an effect error that someone else should get if they have exactly re-implemented your model. This gives you a sense of the reliability by which someone else can assess how closely they have reproduced your results. again, the effect error is bounded in 0 and 2. So 2 is as dissimilar as possible, and 0 is exactly the same characteristic functions. And if you really like the numbers, then as a preliminary assessment to give you a sense of this, we found that we can typically reproduce results really well and capture a lot of differences in models with values on the order of like 0.075, 0.01. And that's what you see here, somewhere on that order. I'm going to stop and explicitly ask, is that clear? Or can I walk through that again to clarify that for some people, or maybe unpack a little bit of this to make it more intuitive?
I have one question, TJ.
Yeah, Bart.
You know, the top, it says the sample size is 10, but the bin looks like there's more than 10 samples there in the top one. I mean,
Yeah, that's right.
Yeah.
Yeah, that's a good question. So the sampling that you see here is sampling all of the possible combinations that you can form of two
Oh.
equally sized subsamples given an original sample.
Oh, okay, okay.
Yeah,
I
and
missed that.
yeah, well, and I don't think I said it. And to make it more clear, this is not all of the possible combinations, because at this scale, I mean, you're talking about trillions of possible combinations, but we impose some algorithmic constraint here where we sample this up to a point to where the distribution that we compute seems to have converged just by continuing the procedure, calculating something like the mean and standard deviation or something like that, and continuing to do so until we have a reliable distribution of the effect error. Yeah, so it's definitely more than 10, but certainly less than all the possible ways that you can divide your original sample. Oh, good question. Anything else that I can clarify for anyone before we move on? I really don't want to leave anyone in the dust here, but also I don't want to get lost in the weeds of things that no one is particularly interested in. So, and again, please interrupt as you feel so inclined. Otherwise, I think we'll just go ahead and proceed. Okay, so having completed this test for reproducibility, that solved our first question. Our second question, how do I package data so that others can reproduce my results in independent study? Having completed this test for reproducibility, I've determined a sample size that's reliable. So the results that I'm publishing or submitting to biomodels in support of their curation process determine that those are reliable results. And so then what information do I need to provide along with that to enable someone else to curate my model and reproduce my results? And we call this the effect report. And this is a verified list of the minimum set of information required to accompany something like a biomodel submission or a journal publication. This is all of the information required for someone else to just read your model off of a paper, allegedly follow all of the procedures that you've described in your the description of your simulation experiments, produce their own sample, and then test whether or not they have actually reproduced your results. Some of this is really technically specific, and some of these terms we have not touched, and I don't plan to. If you're interested in these details, again, there's the link in the paper, and maybe more importantly, my email is throughout the slides, and I can provide it again as well. Suffice it to say that it is possible to package a minimum set of information that can accompany a biomodel submission or a journal paper to do this test by a curator and show quantitatively how well someone else can reproduce your results. A nice feature of this is that this report does not include packaging all of your simulation data, which is especially important if we're talking about sample sizes on the order of thousands. The storage can get pretty obnoxious pretty quickly. One of the bits of information that is stored is the computed empirical characteristic functions. So it's certainly not a small amount of data, but not nearly to the scale of your original simulation results. course, some have advocated to just make all simulation results available, and I'm not advocating one particular stance in that regard. Just in our case here, it's possible to package all this information, and it does not include sharing thousands and thousands of simulation replicates worth of data. Our last point, the curator's problem. Given a sample has published in a paper, and now in the context of what we've covered so far, given an effect report, how then can I re-implement the model that I'm interested in and that I'm curating, generate my own sample, and then show quantitatively how well my sample is the same as a sample of interest. So this is demonstrated here on the right, but the procedure is fairly straightforward. So the effect report includes information about what the sample size is of the corresponding empirical characteristic functions that are included. And so what a curator does is they take their implementation of a model, they generate a sample of the same size, they perform their own test for reproducibility, and then perform a statistical test that we have defined for this problem, and essentially perform a hypothesis test and calculate something like a p-value, and then either accept or reject the hypothesis that I think the curator's sample and the reported sample from a modeler came from the same underlying distribution. If that's not particularly intuitive for you, there's a visualization here of this process. So in the left and right, so this is a simulation of doing the modeler and curator's workflows for the same model and for different models. So here, this is the workflow where the modeler and curator do actually implement the same model. This one is a case where the curator actually implements a different model than that of the modeler. And this first plot here in orange, what you see here, this is results from performing the test for reproducibility as a function of sample size. And these bars that you see are 3 standard deviations of the sample effect error per sample size. And as we would expect, the effect error continues to decrease as sample size increases. And then the blue line here shows the effect error of the curator performing their workflow and then testing the difference between their sample and the one reported in the modeler's effect error. And you'll notice here with this acceptance p-value that's calculated here, this is using a significance level of 0.05. We reject that the samples are the same when this computed p-value is below that threshold. Then you may notice a pattern here where when the effect error is approximately the same, the p-value is always above the orange line. Whereas over here, when the models are different, first you'll notice that when sample size is small, it's not possible to actually show that results are different. It's because the sample size is too small. Whereas with increasing sample size, you'll notice that the effect error during curation continues to remain high, and we get a corresponding p-value that tells us that we should reject that results are the same.
You have a question?
Question, anyone?
Hello. Thank you very much for your talk so far, but just for on the graphs, the top 2, why might be a dumb question. Why are there error bars on the orange but not the blue?
Yeah, it's a great question. So the reason for this is because the error bars are showing the statistics of the modeler's test, or I think it's the curator's test for reproducibility, which is repeatedly sampling the effect error because one randomly divides their original sample in lots of different equally sized subsamples. And so you can get effect error values that are about some mean with some variance. Whereas when performing the curator's step, all the curator does is takes the empirical characteristic function values from the effect report and then computes the effect error against one of their empirical characteristic functions. That's the whole point of doing the random sampling of the effect error in the first place when testing for reproducibility, because depending on how you divide up your sample into two subsamples, there can be some variations just by virtue of that your results are stochastic. This is one of the main points for choosing a sample size that allows reliable determination of whether samples are the same. Does that answer your question? Is that clear?
Yes, thank you.
Great, thank you. All right, if there are no other questions, we can continue. I think from here on out, we're mostly just surveying what can be done. And if we have time, we can glance for a couple of minutes at a little bit of example code that's available. We've generated a graphic to try to embody this entire process. What we really envision here is something like pervasive reproducibility of stochastic simulation, regardless of even the scientific domain. Stochastic simulation is not something that is limited to just modeling in the life sciences. It's done commonly in finance and otherwise. What we really envision is demonstrating quantitatively how reproducible each other's results are as community level practice. This graphic here conveys a sense of what this should look like in practice. I'm going through the entire process from developing a model, demonstrating how reproducible it is, all the way to testing for reproducibility in independent study. As we discussed a few minutes ago, there is a dependence of the ability to detect differences in samples on sample size. I mean, we've done some pretty extensive numerical experiments to try to capture this. And this, again, is a subject of ongoing work. Testing models that are just structurally different. And obviously, so this doesn't require going through some big rigorous process to look at this. And I mean, if you really want to be absolutely sure, you can compute some effect error or otherwise to just say that you did, and so that you can sleep at night. But in a lot of cases, it's sufficient to look at structurally different models that have, you know, just obviously different results, and just say that they're not the same. But in other cases, there are harder problems that I think are important, like detecting differences in individual parameters. Say you're reproducing results in a published paper and you input one of the model parameters from their tables, and you enter a typo. What's the likelihood of you actually being able to determine that you use the wrong parameter value? Or maybe more importantly, what's the likelihood, what is our ability to detect whether results published in a paper are actually different from the ones that are reported in the details of that paper? Differences in parameter values, in some cases even differences in the structure of a model. So we've done a lot of experiments to try to get a sense of how accurately we can do this, and this is here personified here on the right. So this is another case of taking a simple ODE model, randomly sampling it and increasing sample size. What you see here on the right, I'm trying to break this down a little bit. So this is computing the effect error that a curator would get as a function of a difference in one parameter. It's the same model, same simulator, all antimony and libRoadrunner, but just changing the value of one parameter between the modeler and the curator. Now, as a function of the size of the sample, at what point can a curator no longer be able to tell that there is a difference in the models? And this is what's demonstrated here. So these gray blocks that you see in each of these rows, this is showing the mean plus 3 standard deviations of the effect error during the curator's test for reproducibility, which above this gray block is when p-values start demonstrating that samples are not the same. So in general, you can associate that effect errors above this gray block would be rejected. Samples are not the same. And here on the left, 0.5. This demonstrates the curator using a model with one parameter that's been decreased by 50%. All the way on the right, that same parameter has instead been increased by a factor of 2. So it's actually 100% increase. Sorry for that. And then intermediate values in between. One is using the same model, same parameters, same everything. And what you'll notice is that for a small sample size, we can detect relatively large differences in individual parameters, but not ones that are close to the same, but not the same. And as we increase sample size, we become increasingly able to detect smaller and smaller differences in individual parameters. Hence, our sample size and corresponding effect error and distribution, as those increase, our determination of whether two samples are the same becomes increasingly reliable. Of course, with the cost of that, it takes more computing resources and time to generate increased sample sizes. And this is the trade-off here. How large of a sample size can one generate given certain resources to accomplish, say, some sufficient effect error so that others would actually believe when, say, a curator says they've reproduced results, because there is some inherent error here, and that is unavoidable. Question is, how much are we willing to tolerate? This is a current activity of ours in a couple of different fronts. And I'd be happy to discuss some of those details if anyone's interested. Otherwise, I'm just gonna demonstrate some cool use cases with a bunch of different methods. So the second link that I provided in the chat, SSR Project 2024. So that is a repository just with all of the implementations and results. All of the results you see here, at least for the ODE models, are all available and executable at that repository. There are more than what's just demonstrated here, but I wanted to at least give you a sense of some of the use cases. So back in Connecticut at Combine 2023, we made a list of all the difficult models in terms of reproducing stochastic results, and then just went down the line and started generating use cases. So we have really volatile, like complicated, noisy simulation results. Here and here, we've got oscillators, bifurcations, we've got pulses, oscillators, same behavior, same performance for the effect error. The sample size to produce a given effect error will depend on the consistency of the results, but generally we always see this behavior where we get some log linear relationship between sample size and corresponding effect error in the test for reproducibility. We've tried this with agent-based models. 30-second backstory. My group here in Florida, just over time, have accumulated a number of different implementations of a classic example that's distributed with NetLogo, which is the grass sheep wolf agent-based model. We went through and generated up to 20,000 simulation replicates of different implementations in Python, MATLAB, and NetLogo, which for a long time here has been used under the assumption that they are the same, but always with the suspicion that maybe they weren't. And then just went down the line, performed our workflows, and showed that all of the results from the different implementations, all of those are reproducible, but certainly they're not the same. They do not produce the same results. They may qualitatively have some of the same oscillatory features and steady state behaviors, but at the end of the day, they are different models. No getting around that. Very recently, we've been incorporating some of this work into James Glazer's OpenVT project, which James is up next in talks. This is a sample of what some of these results look like. So I'm contributing to a project on single cell migration. And this is an example of what this looks like in CompuCell 3D. We have a number of software projects that James has recruited to participate in this. Artis2, Morpheus, Physicell, TissueForge. All of us we're implementing presumably the same models in our different frameworks and doing some interesting stuff with model specifications. But one of the interesting questions that comes up is, if we do all implement the same things, allegedly, do we actually get the same results? And we're incorporating this capability to do those tests and quantitatively test how well each framework does actually produce the same results. These are some samples here generated from CompuCell. So this is just testing. This is tracking the coordinate of the center of mass of this cell, multiple replicates first with just a random walk. This is a coordinate along the horizontal direction here on the vertical. Random walk is just noise over time, but with some persistent motility model moving from left to right, which is what you see here. You see this gradual increase in the coordinate along the horizontal direction. During my validation of all these workflows, I just did one of these tests with the random walk model and just asked the question of, for all of the CompuCell model mechanisms that are in the random walk model, how well can I actually detect differences from different implementations? So I take one of the model mechanisms in CompuCell, simulate the random walk, but increase one of these particular model parameters. I honestly don't remember which one it was. But most importantly, at what point for this given sample size of 500 can I actually detect that my random walking cell is actually randomly walking in a different way as a function of differences in one model parameter? And you can see a really good example here of the dependence of sample size on accuracy. So this is a baseline simulation, and then doing that again, perform the test and get a p-value of 1. These results are equal in distribution. This doubles whatever model parameter it was that I was varying, performed the same test, and I got a p-value of 1 anyway, which is a false positive. Whereas when increasing that parameter even more, eventually I can find a point where my sample size is sufficiently large to test a difference in model parameters. Done this with stochastic Boolean networks. Pulled an example that this is done with Mabos, and pulled an example from what they provide on their website on NF kappa B sulfate decision. Process works the same. And I think we don't have really any time to actually get into this, but I do at least want to click over and at least give a sense of if anyone's actually interested in looking more into this and maybe using some of this. So this is at the last link that I put in the chat. When you land here, you'll notice that there is actually not really much here, and that's because this is a really new project. This is the start of our effort to develop something that's, I would say, well inspired by like the libSBML and libsetml projects. But in this case, we are porting code over from the original project code. And so if you actually want to look at what this code looks like and maybe even use it or check out some of the examples, you can find it currently on the port branch. That's not the final resting place of this code. Eventually it will be in main. So people watching this video a year from now, look in main. But for those of you right now who may have followed the link, look on the port branch, and you can find a number of Python scripted and Jupyter Notebook rendered examples in the examples directory. So you go to examples and then Python. You'll find some Python scripts and then equivalent Jupyter Notebooks in the notebooks directory. Each of those has been executed and rendered. There's a I say for anyone who's interested in just like the fundamental aspects of this to try to get a sense of the mathematics and statistics, the distributions Python notebook is a really good place to start. And this is actually the script that I used to generate some of the very early examples at the beginning of our discussion. So you may recognize this plot in particular here. But this just essentially walks you through generating probability distribution functions with the same summary statistics, sampling them, and then most importantly, we go all the way, I think, up to the top. You'll see import libssr. And that's the Python package that is implemented in this repository. And you will find later in the example instances of actually libssr.ecf computing empirical characteristic functions. There are a number of features we've provided already to quickly generate empirical characteristic functions, compute errors when comparing them, and even automating the test for reproducibility. You can see a plot here of showing effect error when computing the differences between samples from those different distributions that have the same summary statistics. Again, to give you an intuitive sense of how well we can actually quantify these differences. There's also some demonstrations of what these characteristic functions look like. This is not a mathematical object that I was familiar with until I dug into the literature. So if you're like me and have no idea what these things are, part of the point here is to give you a sense of like what is the actual data that's being generated here. And then very last point in my last minute, now that I'm at the end of my time, there's reproducibility IPy notebook. So this is an actual walkthrough of the entire process of a model or generating a sample, testing for reproducibility, even generating an effect report. All of this is defined in libSSR. So packaging data in the effect report and then the handoff to a curator. You may recognize these results from previously. This then is the stage of the curator actually testing for reproducibility, or testing whether they've reproduced results when using the same model and also a model with a difference in parameter. So that whole workflow is all demonstrated in this notebook. Again, that's reproducibility done by notebook. All right, I'm at the end of my time. I think Bart, I should turn it back over to you. Is that correct?
Well, yeah, but just want to make sure, is there anybody have any more questions?
This is my
And
email.
thank you very much, Tim.
Yeah. Thank you again very much. There's my email. Again, if you're interested in any of the minutia, whether it's the math or stats or software, there's a lot of ongoing work in a number of different directions here. In particular, the libSSR repository. Feel free to reach out. Feel free to jump onto the repository, make a fork, and yeah, I'd love to hear from you.
No more questions? Well, all right. Thanks again. Okay, let me stop the recording and move on to